All right. Good morning, everybody. We are continuing our discussion on antiderivatives, also called indefinite integrals. Let's get ready here. Where's my pen? All right. So just a reminder, when we have the sentence, the antiderivative of, let's say, let's make it simple. Let's say 3x squared is, in this example, x cubed plus c. That sentence we just write in a short, compact way and call it the indefinite integral. So this is my integral sign saying the words the antiderivative of. Then I need to know what is my function in question. Then I end that with a reference to my variable, x in this case. It always has a d with it. And then I say the answer. All right. So the concept doesn't change, just how we write it is a little bit more efficient and compact. Then we said, okay, fine, we can reverse the basic properties up to the power rule by guessing a little bit. It's not really guessing, it's educated guessing, I suppose. Using our knowledge of derivative properties and just understanding that we're now doing it in reverse. So we had a fair number of examples on that. Then we realized that, let's say it like this. When I have a chain rule situation, reversing the chain rule is not as simple as the basic properties, which is understandable because it's a much more complicated derivative property. So reversing that would understandably bring some slightly more complicated looking things. For example, if I have the perfect situation where I have a function of a function, for example, let's say it like that, x cubed plus x, and I have something ridiculous here as my outside function. Let's say, what did we say last time? Let's say this time to the 7. The function of a function can't stand on its own because this is now the result after the chain rule is applied to something. I get a result. So the chain rule is going this way. And understanding the chain rule, it takes a single function of a function and creates two things. The first part of the chain rule and the second part of the chain rule. All of this together is the chain rule. So the second part of the chain rule has to be visible when I'm doing it in this first case, when I'm doing it in reverse, it has to be visible. So I would have to see a 3x squared plus 1 there as well. To then say, if I guess x cubed plus x to the power of 8 has to be there, and that's going to be my first guess. If I try this, yes, it's a function of a function, so the chain rule works this way and creates two parts. The first part is the derivative of the outside function. Okay. Second part is the derivative of the inside function. 3x squared plus 1. I see the key pieces there. I just need to check my number in front, just like the usual correction of the power rule in reverse. So some basic things are still there, even in this reverse chain rule guess and check situation. I do need to see these key pieces, and the chain rule goes from 1 function of a function to 2. One of them is again probably a function of a function. So when I look if this is a reverse chain rule situation, I look to see is there a function of a function in here. It doesn't have to be the whole thing, but some of it. Then accompanying that should be this second part of the chain rule that I need to reverse the chain rule. And I can then say, oh, my antiderivative is 1 over 8 x cubed plus x to the power of 8 plus c, of course. And I can check it. I get exactly what I should get. Now, in this situation, it is fairly obvious that I have a function of a function. It doesn't have to be a bracket to a certain power, of course. I can have maybe a square root x plus 1, let's say, dx. Now let's just first go back one and do two versions of this. Let's make that an x squared and then put a 2x there and finish it. I see I have a function of a function. There's other stuff there, which makes total sense because of what the chain rule does, and I'm doing it in reverse. So my guess, or guess and check at the same time, well, perhaps I don't love the look of this, just like normal roots. Don't love how that looks. Maybe I like the power of 1/2 instead. Then it looks a little bit more familiar, like the previous example. So I'm gonna guess I need an x squared plus 1 to the 3 over 2. Let's see how far that gets me. Well, power rule, 3 over 2 for the first part of the chain rule, x squared plus 1 to the 1/2. It's good, good. Times, says the chain rule, the derivative of the inside function, 2x. Oh, perfect, perfect. But there's no 3 over 2 here in my target. So I put a 2/3 in front to catch that number that the power rule is bringing out. Okay, so I do see the same things repeating over and over and over a little bit, even in this more complicated situation. And I can say the antiderivative is my updated tested function, of course, plus c. Let's just move this up a bit. I could also have something like this. Let's just have the square root of x plus 1 and then nothing else. Now you might think, oh, but you said I have a function of a function to see and something else, and I don't see anything else. That something else is not necessarily visible because sometimes it's a 1. Because if I now write this as x plus 1 to the 1/2 for convenience, and I start thinking what could work here, It has to be x plus 1 to the 3 over 2. Let's see how close we get. Outside function, 3 over 2, x plus 1 to the 1 half. Inside function's derivative, says the chain rule, but in this case it's a 1. So the 1 is there. I just didn't necessarily have to see it. There is a second part, it's just so simple. And of course I make my correction because I don't see a 3 over 2 there. So this is then 2/3 x plus 1 to the 3 over 2 plus c. So yeah, for the more complicated functions of functions, I will see two parts, but not every single time. And I'm still in this reverse chain rule situation. It just depends on the complexity of the inside function. Now, I could also have a function of a function hide in an exponential function. Now, we've seen this one before, but technically we are in the reverse chain rule situation. So how is this one different? How is this one different? Well, it is and it isn't. What sometimes happens is as the second thing that I'm seeing, what is that? This is my function of a function, right? And I don't see anything else. Why not? Because that second part that I should see when I reverse the chain rule, I'm going to have a check. I'm going to have e to the 3x. The chain rule says the derivative of the outside function times the derivative of the inside function. Derivative of the outside function is e to the 3x. Derivative of the inside function is 3. Sometimes, well, when the second part of the chain rule is just a number, that number isn't always visible. When the second part of the chain rule is something involving an x, then there is no choice. It has to be visible in the integral from the start. Like over here, there was a second part of the chain rule that involved an x. That x has to be there. There's no other way. Over here, there was a second part of the chain rule that was a 3x squared plus 1. In some way, that has to be there, visible, present in the integral. But in simpler cases, the second part of the chain rule is just a number. And I don't see it there. Now we could go the same route as the reverse power rule, and there definitely is more than one way to go here, but to be consistent, I want to go this way, the following. I want to see both parts of the chain rule in my integral question, excuse me, question portion. So what I'm going to do is I'm going to say, okay, fine, e to the 3x. I want to see a 3 here. I can't just put a 3 there. That'd be great, but now I'm changing the question. So what I'm going to do is I'm also going to put a 1/3 with the 3. So now I just multiply by 1, so I haven't changed anything. Just like the constant times a function property, any number can be moved to the front just because of the constant times a function property. Then those properties still apply even in reverse. So that now I can focus on reversing the chain rule exactly the way I want. Then you see here in the box, my target has two parts. My target has two parts. It's perfect. And my answer is then the 1/3 was sort of the price I had to pay to make my target look more like the chain rule's result would look. I had to pay a price to get that 3 in there. It's not a big price, just a number, but it does change the answer and it needs to be there. My antiderivative answer is then 1/3, whatever this guy was, e to the 3x, and of course plus c. So this might look a little confusing at the start. Well, guess and check is always going to be a confusing, inconsistent method that only is something reliable in the simplest of cases when something is introduced, when a type of problem is introduced. Sure, elementary school, guess and check, see what happens, play around with some things and see how you can tweak it. But it's only going to get me so far. I want to have a more systematic recipe, procedure, stepwise method to avoid this possible variations between guessing and checking in from one question to the next. So let's make a new page first. So a more structured uh, method to handle this is called the method of substitution. Method of substitution. Now, this method, once you get the hang of it, is just uh, so useful. And it's not long, it's short. What it's essentially trying to do is it's trying to handle the reverse chain rule for me in the background. Without me actually thinking about the chain rule, it's going to do the chain rule in reverse for me. And that is just exactly what I'm looking for. Because looking at the chain rule directly is where confusion could creep in. If the chain rule can be done for me without me even realizing it, that is just wonderful. So let's go back to something simple. Something we started with. Let's say x squared plus 1 to the power of 7 times 2x, and my integral of that. Now, the method of substitution is going to do three things. No more and no less. I'm always going to write three things on the side that helps me rewrite this integral into something that's not as chain rule heavy. And the words that help me remember it are let, then, so. I'm going to use a new variable. I'll call it u, and I'm going to let that represent the inside function that I see in the function of a function portion. In, in this case, it's obviously x squared plus 1. Sometimes the inside function is a little less obvious to spot. It doesn't have brackets and stuff like that, but it's always going to be an inside function as my choice for the substitution. Then I'm simply going to take the derivative of this inside function. So du dx is 2x. Now, the method of substitution is not there to be extremely proper and technically perfect in following the rules. It's there to get the job done. If I write these things in the perfect and most proper way, it's going to look just very difficult and to understand. This method is trying to make things easier. So in that, we are going to use a little trick where we are going to see this little d notation as an actual fraction of what we call differentials. There are ways to show that if I see this as a fraction, these little guys, du and dx, featuring there, they follow the same rules as if they were separable fractions, separable pieces of a fraction. So what I'm going to do is I'm going to see that as a fraction and multiply both sides by the denominator to get du that equals 2x times dx. It's not technically something we feel we can do because originally we said the little d notation is just a name. It's not a fraction. Turns out that I can see it as a fraction and the arithmetic still works. And in this case, it makes things very convenient for me. If I now look at this first step and the last, or the first line and the last of my 3 lines, I'm gonna I can use those 2 lines to rewrite this integral to be a new looking integral, but with the variable u instead. How does that work? Well, I simply rewrite everything. Every x thing has to be swapped out for something with a u. This x squared plus 1 to the 7 is now going to become u to the 7 because u is x squared plus 1. This last line says if I see a 2, an x, and a dx, I can swap them out and change them for a du. I see them exactly there. So different portions become different things, but in here, notice that I have no x anywhere. No x features in this new version. And these are exactly the same. The difference is in how they look and how convenient they are to work with. The first one, I saw a function of a function, and I couldn't stop thinking about the chain rule. But the second one, if I forget where it came from temporarily, it's a very basic antiderivative I'm looking for. My variable just happens to be u. I'm back to basics. U to the 8th, 1 over 8 plus c. So with the substitution, I was able to just forget about the chain rule a little bit and just think about the reverse power rule that is easier and I'm more comfortable with. However, this was just a detour that I can choose to take. My original question used the variable x, and it asked for this first line antiderivative. So I should go back and answer in that same variable. But that's not very complicated. I just swap back what u is in terms of x. 1 over 8, u to the power of 8 becomes x squared plus 1 to the power of 8 plus c. Now, for this level of complexity, you might think that, okay, sure, I could have just guessed and checked my way through this, and with more experience, the guess and check can get me seemingly very far. But the more complex ones are just waiting around the corner to catch you, and guessing is just not as efficient after a while. Whereas this method of substitution is never going to fail me if there is a reverse chain rule situation. It's in this one where its power lies, that it's allowing me to find an antiderivative. The antiderivative step does not involve thinking of the chain rule. Yet when I go from the first to the last, I have reversed the chain rule. So it's very, very effective in the sense that it's hiding the complexity for me. So now it's just a matter of practicing this. I want to show one more example, just a little one, e to the 3x, where I don't see a bracket. I still have to identify when is substitution appropriate, when I have a function of a function. So I'm going to say let, what's my inside function? My inside function in this case is 3x. So that's going to be my u, then the derivative is 3. So I separate the differentials and get this. Now the first and the last line is the key to telling me what I need to see to bring in all u's. I need to see a 3x. Okay, sure. That guy is my 3x. Good. But I also need to see a 3 and a dx. I don't see a 3. So I'm going to bring in a 3 because my right side key tells me what I need. I need a 3. But I can't just make a 3 out of thin air. I need to balance it by paying the price. That 1/3 price doesn't play a role in my antiderivative. So I leave it in front. It does need to be there in my answer, but it's not going to play a role right away. Now I'm able to follow the key on the right and get rid of all the x's and bring in u's. The 1/3 I just drag with me. E to the 3x become e to the u. 3 and dx become du. And now this is an integral, an antiderivative question entirely in a new variable. So forget where it came from. This antiderivative with u as my variable is simply e to the u, of course, plus c. Now I can look back, say, okay, where did this come from? Oh, x, so I need to go back to x. 1/3 e to the 3x, because u and 3x are the same, plus c, done. So the substitution method tells me exactly what I need to do and helps me to not actively think about how to reverse the chain rule. It's doing all of that in the background for me. Let's make a new page. So let's look at some problems. In 12.3, use a substitution variable u to rewrite the given integral in terms of u. Now, let me just see what kind of problems we have. This one doesn't ask us to solve it, though that is ultimately our goal. And then we just have more of them. Okay. I don't see any benefit in not solving them, but I will say that a test question could potentially just ask for you to write the substitution, the 3 points on the right, not finish the whole thing. So read the question carefully, see how far do I need to go here. We'll just go all the way for practice. So there's no reason to not start with number 1. 3x squared minus 5, 12.3, number 1. What did I just say? I just said it. 3x squared minus 5. 3x squared minus 5, I believe to the power of 4, and then a 2x. Double check. Looks good. So with enough practice, you start to see what do I watch out for? What's my thought process here? If I see a function of a function, it's substitution. Let u be my inside function, which is obviously 3x squared plus 5. Then the derivative is 6x. And so if I separate the variables, I get 6x dx. This is going to be my key to tell me how to get rid of x's and bring in all u's. Did I not look at the right question? 3x squared minus 5 to the power of 4. Oh, it's a minus. Okay. Eh. Minus. Minus. All right, thank you. 3x squared minus 5 to the power of 4. 3x squared minus 5 to the power of 4. Okay, good. Perfect. But our key, luckily, on the right, those are still the same. Okay. So now, before I can bring in the u's, I need to check, do I see all the pieces that the substitution requires? Well, the 3x squared minus 5, yes, that's over there. I have a 2x and a dx. I need to see a 6x and a dx. So I need to bring in a 3 times 2 to make a 6. I'll write them separately. I need to bring in a 3 times 2 that's already there, and I need to pay the price to do that. Then this becomes 6x that I need. So sometimes the numbers need a little tweaking in order for me to see exactly what this substitution key needs to see. So 1/3 integral of, it's going to become u to the 4. 6x dx is perfect to swap it out with a du, and I'm good to go. Now, when I look at this, I do not see anything else. It's as if this is a brand new antiderivative question that I do forgetting anything else. So when I do that, the 1/3 stays in front. It's reversing the power rule. So it's going to be u to the 5 with a 1/5 correction, of course, plus c. After I've done that, then I look back to see, oh, I need to go back to x. Now it's just a formality. I almost make a point to not simplify or do anything. All I do is swap back for u what it represents in terms of x, and I do nothing else. Now, of course, we can check this as well, right? Nothing changes in that sense. I can always check my answer. If I take the derivative of this, hopefully correct answer, but let's suppose I'm not quite sure. I'm a little bit hesitant. I don't really have to write the c because it's always going to be a 0. I have my 1/3. I have my 1/5. Constant times a function keeps it in front. Now I have to take the derivative of this function of a function, which will be 5 times the bracket to the 4 times the derivative of the inside bracket function, 6x. Let's scroll up a bit. I don't want to scroll up too much. I want to see my target. So the 5 and the 5 cancel. The 3 and the 6 simplify to leave it 2, and the pieces are exactly like they are at the top for what I need to get. The difference here is, whereas guess and check can seem a little up and down. Sometimes it's obvious, sometimes it's different, sometimes it's more complicated, sometimes it's straightforward. The substitution method is trying to give me some structure. Always follow the same procedure, always go through the same motions. The function can change. The exact substitution choice might look different, but it's always the same procedure, giving me that structure, and by doing that, a little bit more confidence. And the only thing to then do to feel better about the substitution is just practice, practice, practice. Let's see another one. Um, yeah, let's do number 2. I don't want to skip any. Substitution isn't something that comes easy. I see many people in the past hold on too much to the guess and check because that's how we introduce it. But if I have a better tool that's more reliable and safer, I should transition to that. Root 1 minus x. Number 2, root 1 minus x, and nothing else. So that is an ugly x. Let me fix that. Better. So let's see here. I see a function of a function, substitution. Let u represent that inside function. Then the derivative is -1. So separating the variables gives me a negative dx. This is going to tell me exactly what to do. I don't really have to think much about it. It does allow me to rewrite the square root, but in order for me to bring in a du, I need to see a -1 and a dx, and I don't see a -1 there. So I want to correct that first. So I have the root portion. I want to see a -1 and a dx. In order to balance that out, I need to multiply by a -1. And I'll put that in front because that's not really something I'm interested in right now. It does need to be there, however. So I drag that number in front with me when I make my substitution to square root of u, -1 and dx. I can swap that out for a du. Then I just look at this as if it's a brand new integral question. I perhaps want to see u to the 1/2 to make sure I don't make a mistake. I'm just going to do it in one line. That means I have my negative in front. Now antiderivative of u to the 1/2 is u to the 3/2 with a 2/3 correction because there's no 2/3 there. Plus c, and then lastly, I need to go back to my original variable, changing nothing but swapping back what u is in terms of x. So a lot more structure that I can rely on that gives me confidence. And I always write my 3 lines. That's never ever going to change. when we do the very early stages, when we did the chain rule in our derivative properties, we used the substitution as well, but we only did that temporarily, and then we let that go. This one I am not going to let go ever. It doesn't take long to write, and it tells me exactly what I need to do. Let's see. Ooh, let's do number 3. I don't want to skip any of these. Well, I'll skip number 4. That one's a little straightforward. Number 3, x squared over 2x cubed plus 1. X squared over 2x cubed plus 1. Did I remember it right? Oh, beautiful. Okay. So now, in this one, I might not, in the early stages, recognize the function of a function as quickly. Certainly, if I wrote this as x squared times 2x cubed plus 1 to the negative 1, then you would perhaps recognize what to do more easily. But part of the challenge sometimes is to spot the substitution question when it's sort of trying to hide itself, like in this case. Then I'll say, let u represent 2x cubed plus 1. Then I'm just taking a derivative. I'm not really thinking about the question at this stage. It's 6x squared. I'm just separating a fraction. Nothing to see here. Now I'll come back. Ooh, what was my actual question? Do I need to tweak this a little bit? Well, yeah, a little bit. A little bit. I'm going to stick to the top version. I can handle the denominator. The numerator needs a 6. So let's give it a 6. Let's give it a 6. I can tweak numbers because of the constant times a function property. I just need to make sure it balances out to still have essentially my original question. I can't change the original question. Then I have my 1 over 6. Now, bottom first. Denominator becomes just u. The 6x squared plus, not plus, with dx, third line says that's a du. Now, if you write a du there, you're totally fine to do that. I choose not to because in this early stages, it can look a little bit strange to some. Instead, I will always put my differential at the end to help me recognize what to do with the antiderivative question. 1 over u, oh, that's natural log of u plus c, of course. And then I need to go back to what u is. That's just a simple replacement. I don't look at anything else when I do this. I just put it back and I'm done. I can take the derivative of this answer, check if I get the original back way up here. That's always an option, even though we don't do it every time. So sometimes the choice for my substitution is hidden. What is the inside function? But let's just suppose you didn't know. I don't have a reverse quotient rule. There isn't much I can do here because the denominator has multiple terms. So for us, it's actually quite convenient that we have our basic properties, reversing the power rule, tweaking a number strategy, and then we have substitution. We don't have anything else. We don't have a reverse product rule, a reverse quotient rule, or anything like that. So don't try and make those up. If the denominator was a single term, sure, I could separate them and simplify it, and we've done those examples. This one is not. So I don't have a choice. It's going to have to be substitution. Those are the only two tools I have. So if I try, now I see, okay, well, it's either the top or the bottom for my substitution choice. Even if I guess randomly and I choose the top one, then the derivative is going to be 2x. And so I separate them, 2x dx. You see there's nothing in this key that helps me with a denominator 2x cubed plus 1, telling me that that is not helpful. It's not the way to go. It is a substitution, it's a choice, but it's not one that helps me in this case. So I try the other one, and then I see, oh, in the third line, the x squared features. So everything in my original integral, everything features in my key on the left. So that's a better way to go. So there are situations where the choice for the substitution, seemingly I have multiple options, but only one of them will incorporate all the pieces that I see in my original question. You can practice the rest for sure and just look at it and see what substitution would I make? How does it make the integral in u look better? And then there are also questions 12.4. That's more of a mix, I suppose. But substitution isn't very far away. We'll do more of these next time, which will be on Monday, but it's worth just thinking.
All right. Does anyone have any questions about substitution? When we look at our schedule, we see that, where are we now? 19th, substitution, right. Uh, I usually like to give 2 days for the substitution, just so you can go and think about it, see if you have any questions, and then tomorrow is more of a Q&A session. I'll just do more substitution problems just so that you can get the hang of it, because it's definitely the biggest section of this last topic. The rest, it's not really anything new, more just variations on this antiderivative. It doesn't get more difficult than substitution. So tomorrow we'll practice some more substitution. Bring your questions, get the most out of that session. Otherwise, that's all we're going to do. If substitution feels perfect for you, well, we're not going to add anything to that. And then we can also see if there are any questions in terms of the upcoming midterm. All right, if there are no other questions, then I will maybe see you guys tomorrow. Until then.